On a summer night in Phoenix, the outdoor temperature is 95 degrees. Inside air-conditioned homes, it's 72. Thermodynamics says that heat didn't disappear, it moved. Every joule of cooling inside requires dumping more heat outside. So where does all that rejected heat go? Air conditioning doesn't eliminate heat. It relocates it using the same physics as your refrigerator. A compressor pressurizes refrigerant, concentrating thermal energy. That heat gets expelled through outdoor condenser units into the surrounding air. What cools your apartment actively warms your street. And thermodynamics demands a penalty. For every unit of heat removed from inside, air conditioners must dump that heat plus the energy used to run the compressor outside. The outdoor heat output exceeds the indoor cooling by roughly 30%. You're not moving heat one-to-one. You're amplifying it. At building scale, this becomes staggering. A typical office tower's cooling system rejects millions of BTUs per hour into city streets during summer. Multiply that across thousands of buildings simultaneously trying to cool themselves during the same afternoon heat wave. Every building solves its own problem while collectively making everyone else's worse. This creates the permanent trap. Hotter outdoor temperatures make air conditioning less efficient, requiring more energy to achieve the same cooling. That extra energy becomes additional waste heat dumped outside, raising outdoor temperatures further. The system fights itself, and physics guarantees the outside always loses. Cities already operate at 5 to 10 degrees Celsius hotter than surrounding rural areas. This urban heat island effect comes from replacing vegetation with asphalt and concrete, materials that absorb solar radiation all day and release it slowly at night. Cities are heat traps by design, even before air conditioning. Then humans add concentrated waste heat, not just from air conditioning, vehicles, industrial processes, power generation, even human metabolism. 8 million people in New York City collectively produce heat equivalent to a small power plant just from their bodies and activities. We built furnaces and moved into them. Air conditioning adoption amplifies this exponentially. In 1960, 12% of American homes had AC. Today, it exceeds 90%. Globally, air conditioner installations are growing at 10% annually, fastest in the hottest cities already struggling with extreme temperatures. The hotter it gets, the more we cool. The more we cool, the hotter it gets. And nighttime offers no reprieve. Traditional architecture relied on night cooling, opening windows after sunset to flush hot air. But air conditioning keeps windows sealed, while waste heat from millions of outdoor units prevents overnight temperature drops. Cities that once cooled at night now stay hot 24 hours. Tokyo demonstrates the spiral measurably. Between 1990 and 2020, average summer temperatures rose 2.8 degrees Celsius. But that's the average. Measurements show waste heat from air conditioning systems contributes 1.5 degrees directly. Over half the temperature increase came from the cooling systems installed to fight it. Phoenix, Arizona went from 400,000 residents in 1960 to 1.7 million today. Summer nighttime temperatures increased 6 degrees Celsius during that period. But rural areas outside Phoenix saw minimal warming. The difference: concentrated urban development and near-universal air conditioning. The city built to escape heat became a heat generator. Athens experienced a deadly heat wave in 1987 that killed over 1,000 people. Air conditioning adoption surged in response. By 2000, Athens was consistently 3 degrees hotter than 1987. More cooling capacity, higher temperatures, greater mortality risk. The solution created the conditions requiring more of itself. Even northern cities aren't exempt. Stockholm's summer temperatures have risen measurably as air conditioning, previously rare in Scandinavia, becomes standard. Each installation contributes incrementally. Millions of individual rational decisions collectively reshaping urban microclimates. Geography doesn't protect against physics when humans change the equation. The International Energy Agency projects global cooling demand will triple by 2050. That's 1.2 billion additional air conditioning units, concentrated in the hottest cities. Each unit will dump waste heat into urban environments already experiencing temperature increases. The spiral is accelerating faster than climate change alone would cause. This creates a grid crisis. Air conditioning already causes peak electricity demand in most most cities. When everyone runs AC simultaneously during heat waves, grids approach capacity limits. More AC means building more power plants, which generate more waste heat themselves. The infrastructure built to solve the problem becomes part of the problem, and feedback loops multiply. Hotter cities mean more pavement degradation, requiring replacement. Hotter cities mean higher water evaporation, stressing supplies. Hotter cities mean worse air quality. Each consequence demands its own resource-intensive response. One thermal problem cascades into dozens of interconnected failures. Inequality follows the heat gradient. Wealthier neighborhoods with tree cover and better insulation stay cooler with less air conditioning. Poor neighborhoods with older buildings, minimal vegetation, and maximum asphalt become heat sinks where AC is both essential and unaffordable. The spiral hits hardest where people can least afford it. Here's where urban physics could work differently. Passive cooling, the architectural approach used for millennia before air conditioning, remains thermodynamically superior. Shade trees, reflective surfaces, cross-ventilation, thermal mass, natural cooling without waste heat. The solution existed before the problem did. Cities like Singapore mandate green roofs and vertical gardens, vegetation that absorbs heat through evapotranspiration instead of radiating it back. Barcelona redesigned streets into superblocks, prioritizing shade and airflow. Melbourne paints roofs white, reflecting solar radiation before it becomes heat. Design choices determine whether cities trap heat or shed it, and air conditioning technology itself can improve dramatically. District cooling systems, like district heating in reverse, achieve far better efficiency than millions of individual units. Radiant cooling, evaporative systems, ground source heat pumps that dump waste heat into the earth instead of the air. The leverage point isn't eliminating cooling. It's changing where the heat goes. But here's the permanent constraint. Cities already built can't be easily redesigned. Replacing billions of individual AC units with district systems requires infrastructure investment cities can't afford. Retrofitting buildings with passive cooling costs more than installing cheap air conditioners. Physics allows solutions. Economics prevents them.